We've covered a lot. The magnetic field H from Biot-Savart and Ampere, the flux density B, the no-monopole law, and all four Maxwell equations in static form. The Lorentz force, the torque on loops, and how materials respond through the relative permeability. Today closes the static electromagnetic block with three final pieces: how fields behave at the interface between two different materials, how we measure a coil's ability to store magnetic flux through its inductance, and where the magnetic energy lives. Imagine two materials stacked on top of each other with permeabilities μ1 and μ2. A magnetic field crosses the interface. What does it look like on the other side? Start with the normal component of B. Apply divergence of B equals 0 in integral form to a pillbox straddling the interface. Why a pillbox? Because we want to turn the volume equation into a surface one. The pillbox is a tiny cylindrical volume with top and bottom on opposite sides of the interface, and its side walls shrink to 0 as the box flattens. In that limit, only the top and bottom contribute, and no flux can leave or enter. Flux in equals flux out, so B1 normal equals B2 normal. Normal B is continuous. Now the tangential component of H. Apply Ampere's circuit law to a thin rectangular loop straddling the interface with its long sides parallel to the surface. Why this loop? Because as the short sides shrink, only the long sides matter, and the integral reduces to H1 tangential times length minus H2 tangential times length, equal to the surface current K enclosed. If there's no surface current, the usual case for non-conducting boundaries, we get H1 tangential equals H2 tangential. Tangential H is continuous. Two rules, both earned from the integral Maxwell laws. Here's a quick payoff. Combine the two boundary conditions and you get the refraction law for magnetic field lines. A B vector in material 1 hits the interface at angle θ1 from the normal. On the other side, it continues at angle θ2. Normal B continuous gives us B1 cosine θ1 equals B2 cosine θ2. Tangential H continuous, remembering H equals B over mu, gives B1 over mu1 times sine θ1 equals B2 over mu2 times sine θ2. Divide the second by the first. The B magnitudes cancel, and we're left with tangent of θ1 over mu1 equals tangent of θ2 over mu2. Rearrange. Tan θ1 over tan θ2 equals mu1 over mu2. This is the exact same form as electric refraction, just with permeabilities instead of permittivities. Field lines bend away from the normal when entering a higher permeability material. That's why iron pulls magnetic flux lines in. Now inductance. Take a coil of N turns carrying current I, and let phi be the flux through each turn. The total flux linkage is lambda equals N phi. Why flux linkage, not just flux? Because if the coil has 10 turns, the same flux is linked 10 times. Each turn sees it. The inductance L is defined as L equals lambda over I. It tells us how much flux linkage a coil can build per unit current. The unit is the Henry. Let's compute it for a solenoid. Inside, H equals Ni, so B equals mu Ni. Flux per turn is phi equals Ba equals mu Nia. Total flux linkage is lambda equals N phi equals N mu Nia. But N equals N times L, the solenoid length, so lambda equals mu n²Ial. Divide by I to get L equals mu n²Al. For a coaxial cable, a similar derivation gives inductance per unit length equal to mu over 2 pi times the natural log of B over A, where A is the inner radius and B the outer. These are the two formulas you'll reach for most often. Finally, energy. When you ramp current from 0 to I through an inductor, the source has to do work against the back-EMF. That work is stored in the magnetic field. Integrate voltage times current over time. The integral of LdI by dt times I from 0 to I gives 1/2 Li². That's the magnetic energy stored in an inductor. Exactly the same structure as 1/2 CV² for a capacitor. Why the 1/2? Because the current rises linearly, so average current times final current gives half the product. We can also express this field by field. The energy density at each point of space is 1/2 B dotted with H, or equivalently 1/2 μH² or B² over 2 mu. Integrate this over all space and you recover the total 1/2 Li². Two views of the same energy, circuit-based with L and I, and field-based with B and H. Both are essential. Circuit engineers use the first, field theorists the second. And that closes the static block. Over the last many videos, we built up electrostatics from Coulomb to Gauss to potential to Laplace, magnetostatics from Biot-Savart to Ampere to the flux density B, and we covered materials, forces, boundaries, inductance, and magnetic energy. Every static chapter of SADICU is now in your toolbox. The course turns next, wave theory, the time-varying case where E and B couple into electromagnetic waves, is a separate series. For the next several videos, we switch to problem solving. Textbook exercises, one per video, step by step, everything explained from scratch. The theory is built, now we use it.